Ever wondered why your phone's navigation app can find the fastest route to your destination, but AI struggles to understand something as simple as a social media network? It's not that AI isn't smart, it's that it's been stuck in a mental rut. For years, large language models, LLMs, have excelled at text, but when it comes to graphs, those tangled webs of connections like social networks, road maps, or even your brain's neural pathways, they've floundered. But a groundbreaking new study is changing that, and it's using a clever trick called reinforcement learning to teach AI to think like a mathematician. Let's start with the basics. Graphs are everywhere. Think of a social media network. People are nodes, friendships are edges, and the whole thing is a graph. But traditional AI, it's like a tourist with a map but no compass. It can't navigate the complex relationships or reason about how nodes connect. That's where this study shines. Researchers created a massive dataset called ERDOS, named after the legendary mathematician Paul Erdos, to tackle this. Why? Because real-world graph data is messy and scarce. Instead, they generated synthetic graphs using computers, creating 50 different tasks ranging from simple node counting to mind-bending problems like the traveling salesman. But here's the twist. They didn't just train a model on this data. They used reinforcement learning, a technique where AI learns by trial and error, getting rewards for correct answers. Imagine a student solving math problems, getting feedback after each attempt. That's what G1 did, but on graphs. The results? G17B, a 3 billion parameter model, outperformed a 72 billion parameter model on graph tasks. And it didn't just memorize answers. It adapted to entirely new graph types, like predicting protein interactions or analyzing social networks. So why does this matter? Graphs are the hidden architecture of our world. From recommending movies to understanding disease spread, graph reasoning is key. By teaching LLMs to think in graphs, we're unlocking AI's potential to tackle real-world challenges without relying on endless human-labeled data. This isn't just a step forward, it's a paradigm shift. By combining LLMs with synthetic data and reinforcement learning, we're building smarter systems that can understand the world's complex connections. And that's a game changer. What do you think? Could AI's new graph skills revolutionize fields like medicine or climate science? Let me know in the comments. And if you want to dive deeper, check the links. Stay curious. Ever wondered how scientists untangle complex networks, like social media connections, city traffic systems, or even the internet? Today, we're diving into the math behind graphs and exploring real-world problems that show how these tools help us make sense of the world. Let's break down key concepts using examples from actual research. First up, strongly connected components, SCCs. Imagine a graph where nodes are cities and edges are one-way roads. An SCC is a group of cities where you can reach any city from any other, like a closed loop. For example, in a graph with edges 2 right arrow 5, 5 right arrow 1, 3 right arrow 4, 6 right arrow 2, how many SCCs are there? Nodes 3 and 4 form a cycle, while others are isolated. That's 6 SCCs, each individual node except 3 and 4, which form one. It's like finding hidden loops in a maze. Next, topological sorting. This orders nodes in a directed graph, so edges go from earlier to later nodes. Think of task scheduling. If task A must come before B, you arrange them in order. For a graph with edges 1 right arrow 6, 1 right arrow 5, 1 right arrow 4, 1 right arrow 3, 1 right arrow 2, the topological sort is. It's like lining up dominoes so they fall in the right sequence. Now the traveling salesman problem, TSP. This classic puzzle finds the shortest route, visiting every city once and returning home. In a complete graph, the minimal cost might be 27. But TSP is super hard for big networks. Scientists use algorithms like nearest neighbor or genetic algorithms to approximate solutions. It's like finding the fastest way to deliver packages without getting lost. What about triangles in a graph? Let's say we want to count how many triangles include node 1. In a complete graph where node 1 connects to 7 others, every pair of neighbors forms a triangle with node 1. That's C72 equals 21 triangles. It's like counting how many groups of 3 friends include your best buddy. Then there's the minimum spanning tree, MSD, which connects all nodes with the least total cost. For a graph with edges 1, 4, 2, 3, 3, 4, 3, 5, the MSD might be. It's like building a power grid that reaches every house with the shortest possible wires. Finally, the shortest path. If you want to get from node 1 to node 5, the fastest route might be. Algorithms like Dijkstra's solve this by prioritizing the lowest cost paths. It's the digital equivalent of a GPS, navigating a maze of data. So next time you see a recommendation, a map, or a network diagram, remember, behind the scenes, AI is learning to see the invisible web of relationships shaping our world. The future of AI isn't just about processing data, it's about understanding connections. Thanks for watching. If you want to explore these concepts further, hit subscribe and let me know in the comments. Stay curious, because the next big leap is just around the corner.